Today we will study some results related to operators on Hilbert spaces. These definitions we have also done in previous lecture, but we are again doing it because we are going to use it in our results today. So if H1 and H2 are two Hilbert spaces and T is a bounded linear operator from H1 to H2, then Hilbert adjoint operator T star of T is the operator such that inner product of Tx with y is equal to inner product of x with T star y. Here x belongs to H1 and y belongs to H2. And if instead of two Hilbert spaces we considered Hilbert space H, then bounded linear operator T from a Hilbert space H to H is said to be self-adjoint if T star is equal to T. And in this case, this inner product will become inner product of Tx with y is equal to inner product of x with Ty, because T star equal to T. And this T is called unitary if it is bijective, means 1 1 and on 2, and T star equal to T inverse. And this T is normal if T star equal to T star T. Also, projection on a Hilbert space H is an operator. We denote it by P if it satisfies P square equal to P star equal to P. So from the definition of unitary we see that because T is bijective and T star equal to T inverse. So it means T is unitary if and only if T star T is equal to T star equal to I. Here I is the identity operator. So it means self-adjoint operator and unitary operator are also normal operator. However, converse is not true. If the operator is normal operator, then it may not be unitary operator or self-adjoint operator. For example, if we consider the identity operator I on a complex Hilbert space, then if we take T to be 2 iota I, then it is normal because T star is equal to minus 2 iota I conjugate of this. And T star, this T is 2 iota I, T star is minus 2 iota I. It means T into T star is 4 iota. Also T star T is 4 iota. Means T star is equal to T star T. But T star is not equal to T. Also T star is not equal to T inverse. Means minus 1 by 2 iota I. T star, if you calculate, it will be minus 1 upon 2 iota I. So T star is not equal to T inverse. So here T is a normal operator, but T is not self-adjoint because T star is not equal to T, and it is not unitary because T star is not equal to T inverse. Self-adjoint operator is also called Hermitian operator. So now one definition. Let T be a bounded linear operator on a Hilbert space H. Then if T is self-adjoint, then inner product of Tx with x is real for all x belonging to H. And if H is a complex Hilbert space, then inner product of Tx with x is real for all x belonging to H, then T is self-adjoint. First of all, we will prove this result. Here it is given that T is self-adjoint. T is self-adjoint means T star equal to T. Now we will show that this inner product is real. This inner product will be real if its conjugate, it is equal to its conjugate. So inner product, conjugate of inner product of Tx with x is equal to inner product of x with Tx. And this will be equal to inner product of Tx with x because T is given to be self-adjoint. In case of self-adjoint, inner product of x with Tx is equal to inner product of Tx with x for all x belonging to H. So we have proved that conjugate of inner product is equal to its inner product. It means this is a real number. Its complex part is 0. Now for the second case, it is given that H is a complex Hilbert space and this inner product is real. Because this inner product is real, so it will be equal to its conjugate. Now we have to show that it is self-adjoint. So because inner product is real, inner product of Tx with x is equal to conjugate of inner product of Tx with x. So because H is given to be a complex Hilbert space, so inner product of we know that inner product of T star y with x is equal to inner product of y with Tx. So here it is Txy. So it will be inner product of x with T star x. It is conjugate here. This is also conjugate. So its conjugate will be inner product of T star x with x for all x belonging to H. So if you shift to left hand side, inner product of Tx with x minus inner product of T star x with x is equal to 0. It means inner product of T minus T star x with x is equal to 0 for all x belonging to H. And this is possible only if this operator is a equal to 0 operator. Or this is possible only if T equal to T star. So we have shown that if H is a complex Hilbert space and inner product of Tx and x is real, then T is self-adjoint because T equal to T star. The product of two bounded self-adjoint linear operators S and T on Hilbert space H is self-adjoint if and only if operator commute, means St equal to Ts. So we have to show that St is self-adjoint if and only if St equal to Ts. So we have to prove two parts here. If operators commute, then St is self-adjoint. If St is self-adjoint, then operators commute. First of all, assume that S and T are self-adjoint operators on Hilbert space H, and S star is, it means S star is equal to S and T star equal to T. Suppose S and T commute, means St is equal to Ts. Then St star is equal to T star S star. Because T is self-adjoint, S is self-adjoint, therefore T star equal to T and S star equal to S. So T star equal to T, S star equal to S. Because it commutes, Ts is equal to St. So Ts is equal to St. So we have proved St star equal to St. It means St is also self-adjoint. It means product of two bounded self-adjoint operators is also self-adjoint. Now converse part. Suppose St is self-adjoint. It means St star equal to St. St star is T star S star equal to St. But because St is self-adjoint, because S and T are self-adjoint, therefore T star equal to T and S star equal to S. So T star equal to T, S star equal to S. It means Ts equal to St. And it means S and T commute. So we have proved that if St is self-adjoint, then they commute. If they S and T commute, then St is self-adjoint. Let A belongs to BH and norm of AF is equal to norm of A star F for every F belonging to H. Then A is normal, means A star equal to A star A. We know that for every F belonging to H, inner product of A star A minus A star F with F is equal to inner product of A star A F with F minus inner product of A star F with F. If you open this, this is A star AF minus A star F. So inner product of A star AF with F minus inner product of A star F with F. And A star A F with F. This inner product can be written as, if you shift this to this side, this will be inner product of AF with AF. This is by definition because A belongs to BH. Therefore, inner product of A star AF with F is equal to inner product of AF with F. Similarly here, A star F with F, this inner product will be equal to inner product of A star F, and this is A here, so it will be A star F. Because A is given to be Hilbert adjoint operator. In fact, bounded Hilbert adjoint operator. So by definition of inner product of AF with AF is equal to norm AF square, and inner product of A star F with A star F is norm A star F square. But it is given that norm AF is equal to norm A star F. So this is 0 square minus 0 square equal to 0. So we have shown that inner product of A star A minus A star F with F is equal to 0. This is possible only if this operator is equal to 0 operator. Means A star A minus A star is equal to 0 operator. And it means A star A is equal to A star. You can shift this to this side. Here it means A is normal. This line is not required here. This inner product is 0 if inner product of A star A minus A star equal to 0 operator, and it means A star A is equal to A star. It means A is normal. So we have shown that if A belongs to BH and norm of AF equal to norm of A star F, for every F belonging to H, then A is normal, means A star A equal to A star. For the second result, T is unitary if and only if T is an inner product preserving surjection. Surjection means onto. Bijective means 1 1 and onto. So inner product of Tx with Tx is equal to inner product of X with T star Tx. This to this. Inner product of X with T star Tx. Because T is unitary, it means T star T equal to I. So it means inner product of X with X. So we have shown that inner product of Tx with Tx is equal to inner product of X with X. It means T preserves inner product. But it is given that T is a surjection. We have to also show that T is a surjection. But by definition of a unitary operator, we know that T is always a bijection, means T is 1 1 as well as onto. So we need not prove anything because T is always onto. We can say T is a surjection. So by the definition of unitary, so hence T is a surjection which preserves the inner product. Here we have shown that it preserves the inner product. Now we prove the converse part. Suppose T is an inner product preserving surjection. Now we have to show that T is unitary. It means inner product of T star T x with x is equal to inner product of Tx with x T. So because it preserves the inner product, hence inner product of Tx with x is equal to inner product of x with x. Or we can say that inner product of Ix with x, where I is the identity operator. Or we can say, if you shift to left hand side, inner product of T star T minus I x with x is equal to 0. And this inner product is 0 only if T star T minus I equal to 0 operator. Or we can say that T star T equal to I. Here it should be equal to I, because I have repeated this part here. T star T minus I equal to 0 operator means T star T equal to I. Because T star T equal to I, shift I to this side. In place of 0 we will write identity operator I. So it will be inner T star T equal to I. It means T is unitary operator by definition of unitary. So we have shown that here we had assumed that T is a unitary operator, and we have proved that T is surjection which preserves the inner product. Here we have proved assumed T to be inner product preserving surjection, and we have proved T is unitary. So it means T is unitary if and only if T is an inner product preserving surjection. Now sequences of self-adjoint operators. Let Tn be a sequence of bounded self-adjoint operators on Hilbert space H. Suppose Tn converges, means norm of Tn minus T tends to 0, where norm is the norm on this operator. Here T is the limit of the sequence, because this sequence converges. Suppose it converges to T, then the limit operator T is bounded self-adjoint operator on H. We have to show that T is bounded self-adjoint linear operator on H. Here we are given that Tn is a sequence of bounded self-adjoint linear operators. It is given that Tn is a sequence of bounded self-adjoint linear operators, and it is from on a Hilbert space H. It means Tn star is equal to Tn. Now we have to show that T is also, it converges to T, and T is also self-adjoint. Let's see, T will be self-adjoint if T star equal to T. So let's see what is norm of T minus T star. If we add and subtract Tn, and if we add and subtract Tn star to this, we are subtracting Tn and adding Tn, we are subtracting Tn star and adding Tn star. Then we know that by triangle inequality, norm of x plus y is less than or equal to norm x plus norm y. So this is norm T minus T star is less than or equal to norm T minus Tn plus norm Tn minus T star plus norm Tn star minus T star. This T minus Tn plus Tn minus Tn star plus Tn star. But Tn is a self-adjoint operator, and therefore Tn star equal to Tn. So Tn equal to Tn star, so this will be 0. So it means this is equal to norm T minus Tn plus norm Tn star is Tn minus T star. We can write S plus T star equal to S star plus T star. So it means Tn minus T star, because it is Tn star minus T star. So it is norm T minus Tn plus norm Tn minus T star, because we know that norm of T star is equal to norm of T. So it means norm of Tn minus T star is equal to norm of Tn minus T. So because norm of x minus y is same as norm of y minus x, so we can write as twice norm Tn minus T. Because Tn tends to T, therefore this Tn minus norm of Tn minus T tends to 0 as n tends to infinity. It means norm of T minus T star equal to 0, and this is possible only if T star equal to T. Hence the operator, limit operator T is a bounded self-adjoint operator on H. Now one more result. If T is a linear operator on a finite dimensional Hilbert space H, then there exists an orthonormal basis for H relative to which matrix T is diagonal. It is given to us that T is normal operator on a finite dimensional Hilbert space H. Because T is normal, it means T star is equal to T star T, where T star denote the adjoint of T. Because H is given to be finite dimensional operator, so and in finite dimensional operator, normal operators are precisely those that can be diagonalized by unitary matrix. So let V1, V2, Vn be orthonormal basis for H, consisting of eigenvectors of T associated with eigenvalues appearing in the diagonal D. That is, by characteristic equation, T Vi is equal to lambda I Vi, where I varies from 1 to n. Let X belongs to Hilbert space H. It means we can write X as a C1 V1 plus C2 V2 plus Cn Vn. Because V1 V2 are the orthonormal basis for H, so we can write X belonging to H as linear combination of these vectors. Here C1, C2, Cn are scalars. Therefore Tx is equal to T of C1 V1 plus C2 V2 plus Cn Vn. Or we can write C1 TV1 plus C2 TV2 plus Cn TVn, because Ci's are scalars. But TVi is equal to lambda I Vi. Means TV1 equal to lambda 1 V1, TV2 equal to lambda 2 V2 and so on. So it will be C1 lambda 1 V1, C2 lambda 2 V2 and Cn lambda n Vn. If we write in matrix form, we can write it as matrix Tx is equal to matrix C1 lambda 1 V1, C2 lambda 2 V2, Cn lambda n Vn. Hence this matrix representation of T relative to orthonormal basis V1, V2, Vn is diagonal, with the eigenvalues T appearing on the diagonal. Now one more result. If P is a projection on a Hilbert space H with range M and null space N, then M is orthogonal to N if and only if P is self-adjoint. Suppose we consider a projection operator P on a Hilbert space H with range space M and null space N. We have to show that M is orthogonal to N if and only P is self-adjoint. So first of all, assume M is orthogonal to N. Now we will show that P is self-adjoint. So for any x belonging to M, and y belonging to M, inner product of x with y is equal to 0 because M is orthogonal to N. This is by the definition of orthogonality, because if x belongs to M and y belongs to M and M and N are orthogonal, then inner product of x with y is equal to 0. Now we will show that P is self-adjoint. P is self-adjoint means P star equal to P, or we can prove inner product of Px with y is equal to inner product of x with Py. This is by the definition of self-adjoint. Because we know that inner product of x with y equal to 0, if we apply the projection operator P on both sides, we know that Px is equal to x because x belongs to M, and Py equal to 0 because y belongs to N. M is a null space and N is a N is a null space and M is a range space. Though Px equal to x and Py equal to 0. Therefore, we can write it as inner product of xy is equal to inner product of x with 0. And this can be written as x equal to px and 0 equal to py. So inner product of px with y or inner product of x with py. So it means P is self-adjoint. Now converse. Suppose P is given to be self-adjoint. It means by the definition of self-adjoint, inner product of Px with y is equal to inner product of x with Py. Here x belongs to M and y belongs to M. Because P is a projection, so and x belongs to its range space and y belongs to the null space, therefore Px is equal to x and Py equal to 0. If we substitute these values here, then we will get Px equal to x, inner product of x with y is equal to inner product of x with 0. Inner product of x with 0 is equal to 0. It means inner product of x with y equal to 0. It means because x belongs to M and y belongs to N, so inner product equal to 0 means M and N are orthogonal. Thank you.